So let's look at a couple of examples, because I definitely have seen in many people's homeworks questions like trying to disprove a limit using the limit definition. So let's look at something like this. Let's prove. I need some more black pens. We're going to prove that the limit as x approaches 2 of 3x plus 1 is not equal to 4. I mean, and I think it should be relatively obvious to us that it's not 4, because if you plugged in 2, you can get 7. But how do you actually use the precise definition of the limit to prove that the limit doesn't exist, or isn't what we're saying it is? So you could look at this graphically if you really wanted to. I think we've got an idea, right? That like, so if my function was 3x plus 1, and if we were zeroed in on 4, that the corresponding x value would be 1. And so if we're over here, right, and so if we want to be within, 4 plus epsilon or 4 minus epsilon, our delta would need to be on either side of 1. And if we're way over here at 2, right, we're going to have issues. So here's what I'm seeing. We are not going to be able to find a delta greater than 0 such that if x minus 2 in absolute value is less than delta, and again, that just says x is close to 2, right? If we're within delta of 2, we're living in here. That's not going to put us in this range here. That's a problem, right? Because that's what the precise definition of limit actually says, that we can, if the limit is what we say is, we can find an interval on either side of the thing we're approaching so that our function values end up on either side of the limit we're getting close to. So let me just finish this off here. We won't be able to find delta greater than 0 such that if that's true, then the absolute value of f of x minus 4 is less than epsilon. Right, we're not going to be able to do that. So here's how, if I was trying to prove this thing or disprove this thing, is what I should say. Here's how I would proceed. So I would go about it like a normal proof. We need both x minus 2 in absolute value less than delta, and we need that the absolute value of f of x minus our limit plus epsilon. And then we're going to do the thing where we just kind of work both sides until we isolate x in each equation. It's not terrible. In this equation, it's super not bad. It's x minus 2 is less than delta, bigger than negative delta. And we add 2 to both sides, all sides. And over here, we rewrite this as the opposite value of 3x plus 1 minus 4. A lot of phone calls today. None of them from anyone important, just a lot of phone calls. 3x minus 3, less than delta, sorry, epsilon. So we've got 3x minus 3 less than epsilon, bigger than negative epsilon. And then if we solve for x, let's see, 3x less than epsilon plus 3, bigger than 3 minus epsilon. And then dividing everything by 3, we've got x less than epsilon plus 3 over 3, bigger than 3 minus epsilon. So then I'm going to set, well, really either one. I'm going to set this equal to that and this equal to that. So when I set 2 plus delta equal to epsilon plus 3 over 3, let's see what happens when I get for delta. So I'm going to do a little bit of simplifying here. This is really epsilon over 3 plus 1. And solving for delta, I mean delta equal to negative 1 plus epsilon over 3. Yes, leave that. Yeah, cool. But that's not good, right? If epsilon is less than 3, then delta is going to be negative. That's a problem, because the way this is supposed to work is that for any positive epsilon, we should be able to find a corresponding delta, so that if, I should say, a corresponding positive delta, so that if x minus 2 in absolute value is less than that delta, then you get that the function minus limit is less than epsilon. But we can't, right? There are definitely epsilons smaller than 3 where a delta doesn't exist. I'll say that again. There are epsilons that are positive where delta isn't positive. That means we can't do it, right? We can't do the thing that you're supposed to be able to do to prove the limit. We can't, for some epsilon, find a corresponding delta so that the things work the way they're supposed to work. I wish I had more room on that page. So this shows that the limit as x approaches 2 of 3x plus 1 does not equal 4, because we cannot find a delta for every epsilon such that absolute value of x minus 2 less than delta implies. I should really say we can't find a positive delta, right? I'm always, so whenever someone's talking about delta and epsilon, even if they're not saying it, they mean in their head that those things are positive. And no one is ever saying that in this class, the words epsilon or delta and not thinking, oh, that's a positive thing. It's always a positive thing. So even if I forget to say it, I mean it's positive. So we cannot find a positive delta for every positive epsilon such that this implies this. And that's the whole gist of the thing. We can't do what we want to do. Questions about that? Yeah.
Can you just go over it? So once you set delta equals to epsilon, then you solve for delta. Can you just go over how you got the conclusion again?
How you got which part?
The conclusion. So after you get what delta is, you have f. For if epsilon is less than 3.
Right. So I was looking at this and trying to make it negative. And I know that if epsilon is less than 3, I always hate it when it's 3, because like epsilon and 3 like look the same. It's like which one's which? But sorry, that's what we've got. So if epsilon is less than 3, then we can say that epsilon over 3 is less than 1, and negative 1 plus epsilon over 3 is less than 0. And that's what my delta is. So I was kind of working backwards from that. I was saying, oh, if delta is negative 1 plus epsilon over 3, I can see there are times it's going to be negative. And this is definitely going to be negative if epsilon over 3 is less than 1, if epsilon is less than 3. Does that clear it up a bit?
Yeah.
So I was just jumping to that conclusion because I could see what it was, right? I can see that, oh, negative 1 plus a number less than 1 is going to be negative. So as long as this numerator is less than 3, it's going to be negative. Question, Sophia?
Yeah, so this isn't the same as the inverse value theorem.
No, not at all. This is not the inverse. I think it's the inverse derivative theorem or inverse of value. Oh, you mean the intermediate value theorem?
Oh, intermediate.
Yeah, no, not at all the same as the intermediate value theorem. Definitely not. We can talk about that those today, for sure. Other questions about this? Correct. Yes. Because so the reason delta has to be positive is because what we're saying is that the absolute value of x minus 2 is less than delta. Absolute values are never negative. So this couldn't be less than a negative number. Right? It has to be less than a positive number. But yeah, very, very generally, delta and epsilon always positive. For sure, without a doubt, never, ever, ever negative. Oh, thank you. Yeah, of course. Never hesitate to let me know that the paper is in the wrong spot. I could do something. Let me zoom in a little bit. Manual zoom. All right, great. So as much as I would not love to do more of those. They're not they're no one's favorite. This is everyone's like least favorite part of taking 21A usually is delta epsilon proofs. Let's do one more. And then we'll move on to other things like continuity and the intermediate value theorem. So let's go ahead and again, for this function, f of x equal to the piecewise function x plus 2 when x is less than or equal to 3, and x squared when x is greater than 3, which we can also look at graphically. It looks kind of like this. Let's see, if x were 3, we get 5. Kind of like that. And then x squared after, and 3 squared is 9. Kind of looks like that. It looks better than that, but that's a very, very big idea. And clearly from the picture, we can see the limit doesn't exist as x approaches 3. Right? From the left, it's getting closer and closer to 5. From the right, it's getting closer and closer to 9. So we know the limit as x approaches 3 of f of x does not exist. But we want to prove it. So I want to prove the limit as x approaches 3 of f of x. So there's kind of two different ways you can ask this question. You can either ask it as actually just showing the limit doesn't exist, or you can show, or you can, I'm going to specifically prove that the limit isn't equal to a particular value. So we say, okay, let's prove the limit is not 5. So, okay, how am I going to do this? Well, here's what I can see. So if x is on the right side of 3, we're going to have problems. So here, if x is between 3 and 3 plus a little bit, then the function is x squared. Because we're on the right side of 3, and the function is defined to be x squared when x is bigger than 3. And we can certainly say that the absolute value of f of x minus the limit is, well, I'm just throwing in the values, or I should say the supposed limit, right? It doesn't really exist. Which we know is close to 4 as x approaches 3. So we can say if epsilon is less than 4, say epsilon equal to 1, then here's what's going to happen. We're going to get this limit, this function, this absolute value of the function minus limit, which is the absolute value of x squared minus 5, to be, oh, sorry, yes, of course. That's going to end up being larger than epsilon for any delta such that 3 is less than x is less than 3 plus delta. Right? No matter how small delta is, the function is still going to be too far away from the limit value. Right? We can make delta really, really, really small, but no matter how close we get, right, we're never going to get that function. Whoops, sorry, you can't see the top part now. And no matter how close we get to 3 here, we can't make this function any closer to 5. The closest it gets to 5 is not quite 4. So setting epsilon to be 1 means we're never going to get that close. So we cannot, and obviously we cannot, because if not, we can't show that the limit of this function is equal to 5. Because it isn't. So I should point out, this violates the requirement that we can find a delta for any epsilon such that the absolute value of f of x minus the limit is less than epsilon. Right, we couldn't do it. Oh, sorry, take that last part there. So sometimes people like to ask you to disprove limits. This is kind of the, and it's kind of, I mean, there are different phrasings you can use, there are different words you can use, but the general idea is that you're usually trying to show that no matter how close the x values get to whatever x is approaching, you can't get things to be close enough that way, or vice versa. If things are really close this way in the y kind of sense, you can't make x as close as it needs to be, or x has to be some, or the delta has to be some negative value, like we saw in the previous example. So those are kind of the ways that you can show that the limit isn't what we need it to be. But let's go ahead and move on to continuity, because I think some classes are, well, some classes aside from one are starting to get towards the limit definition of the derivative, I would just imagine. So we should definitely talk about continuity and probably even talk about the limit definition. We'll see. We'll see what we can do. So continuity. Continuity is actually, although very important, is a pretty straightforward concept. Visually, it's, I think, really easy to tell if a function is continuous or not. Let's look at a couple examples. A couple examples of functions that are not continuous. And almost without exception, usually when we're talking about discontinuity, we're using a piecewise function. Here's a function, f of x equal to x squared when x is greater than 2, equal to x plus 2 when x is less than 2. So it looks kind of like this. And then like that. And if only it were defined there, it would actually be continuous, but it's not. So this function is discontinuous at 2. Because f of 2 doesn't exist. So first and foremost, for a function to be continuous at a point, it needs to be defined at that point. That's not the only requirement. We can also have a function that looks like this. Say g of x is, and I actually kind of got that one backwards from what I meant to be. I'm going to switch it up. G of x is x squared when x is less than 2, and it is x plus 3 when x is greater than 2. So this function looks like this.
Let's change it. Hold on.
Greater than or equal to 2. This function looks like that. It's got these y values. If you could plug in 2 there, you would get 4. When you plug in 2 there, you get 5. And this function is definitely defined at 2, right? F of 2, sorry, g of 2 is definitely equal to 5. So great, checks off being defined. That's an important thing to be. But this function is discontinuous because there's a break. Right, from the left side and the right side, we're not getting close to the same value. Or as I would like to say, it's discontinuous because the limit as x approaches 2 of g of x does not exist. There's no limit there. So that's another way. So typically there are kind of 3 different ways we talk about a function being discontinuous. Either the function doesn't exist at the point that you're talking about continuity at, or the limit doesn't exist where you're talking about continuity, or they're not equal to each other. So the other way a function is not continuous is by something like this. If your function is, let's say it's x squared when x is less than 2. It is 7 when x is equal to 2, and it is x plus 2 when x is greater than 2. And this one looks like this. Little parabola to the left of 2. And then to the right of 2, it's the straight function. Oh, yes. But then at 2, it's equal to 7. So f of 2, definitely 7. The limit definitely exists, right? As x approaches 2 of this function, what is the limit? Definitely 4, right? As we get close to 2 from either side, the y values get close to 4 from either side. But, oh, it's not continuous. And again, from a very kind of basic point of view, you can see it's not continuous because when I graphed it, I couldn't graph it without lifting my pen off the paper. I had to jump up there to get that point. It's not continuous because the limit as x approaches 2 of this function does not equal the function evaluated at 2. And really, when we talk about continuity, you can sum it up all in just this piece here. For the function to be continuous, you have to have the limit. I should say, let me just write it down actually. So, definition. F of x is continuous at x equal to a if the limit as x approaches a of f of x is equal to f of a. That's the whole deal. Usually we break it down into 3 things to check. We check that f of a exists. If it doesn't, it can't be continuous because it has to exist to be able to equal something else. We check that the limit exists. If it doesn't, it can't be continuous. And then lastly, we check to make sure they're the same, which really, again, is all contained in this, right? Because if either one of these sides don't exist, they can't be equal to each other. And I'll just point out, if the function doesn't exist and the limit doesn't exist, you can't say it's continuous because a non-existent thing equals a non-existent thing. That's not true. We don't do that. So when you're trying to show continuity, these are the 3 things to check for. Check that the function exists, check that the limit exists, and then see if they're equal to each other. That's kind of it. So, a couple things to be aware of as far as continuity is concerned. Most functions we deal with are continuous on their domains. So I'm going to write a very broad statement. Most functions are continuous where they're defined on their domains. Let me give you some examples. So, polynomials are continuous everywhere. Or as you want to say, on the set of all real numbers. Here's an example of a polynomial. I'm sure you all know a good polynomial. X cubed plus 5x squared minus 4x plus 7. One of many, right? But it's definitely defined everywhere, right? Polynomials, there's no weird division by 0 or square roots of negatives or logarithms of zeros or negatives. Its domain is everything, and it's defined on its domain, which is everything. And every polynomial is defined and continuous everywhere. Some other functions, rational functions, which is a polynomial divided by a polynomial. For example, f of x equal to x squared minus 4 over 2x minus 1. This is continuous on its domain. I don't think there's an apostrophe there. I don't care. It's not a grammar class. So everywhere except for x equal to 1/2, this function is continuous. Sure thing, Rush. Let me just put the page back over a second. To be continuous, and we'll say it again, the limit has to exist, the function has to exist, and they have to equal each other. We're going to write it down again, don't worry. I'm just giving you some examples. So this function definitely continuous everywhere except that it's vertical asymptote. If I was going to draw this, I should have picked something easier to draw. This looks vaguely like, let's see if I plug in 0, I get 4, sure. I don't know exactly what this looks like, but it looks something like, yeah, okay, fine. Trying to like not draw it terribly. I think it looks kind of like this. I don't really know. It probably looks different than that. I'm not super worried about it. The whole point is that at any point, here, here, there, all those points, the function is continuous. The only point it's not continuous at is when x is equal to positive 1/2, where it's undefined. So just a real quick list of the rest of them. Trig functions. All of them are continuous on their domains. So that means that sine and cosine are continuous everywhere, because they're defined everywhere. And tangent, cotangent, secant, and cosecant are defined everywhere except for where, or sorry, are continuous everywhere except for where they're undefined. So except for at their vertical asymptotes. If you think about the tangent function, right? Here's good old tangent with vertical asymptotes at -π/2 and π/2, and then you just keep adding a pi to get all the rest of the range. This tangent function is definitely continuous everywhere except for where it's undefined. And then just a couple more things to add to the list. E to the x, or really any I should say positive base to the x power. Yes. These are all continuous everywhere because they're defined everywhere. And then things like natural log of x or log base 2 of x, those are continuous on their domains, meaning when x is greater than 0. So here is a very, very, I don't want to say short, because it's not really short, but here's a pretty extensive list actually of all the functions we know that are continuous. Again, I just want to point out sine, cosine, continuous everywhere. Tangent, cotangent, secant, cosecant, continuous where they're defined. Logarithms, continuous where they're defined. Rational functions, continuous where they're defined. And then these other ones, polynomials, exponentials, and sine and cosine are continuous everywhere. Or you could also say they're continuous where they're defined, because they're defined everywhere. And most teachers, I think, are usually like, you kind of just get to know that this is true. And you don't have to like prove that a polynomial is continuous everywhere. You just kind of are allowed to just state it. And this is important when we start talking about the intermediate value theorem, because one of the criteria of the intermediate value theorem is the function you're dealing with is a continuous function, at least on the domain that you're, or the interval that you're given. So, yeah, so how to show f of x is continuous at x equal to a. Step 1. Yeah, sorry. I wish I could see it over here, but I can't. That's not entirely true, but seeing it over here is problematic. So the f of a exists. Step 2. So the limit exists. And step 3, show that they're the same. And if you fail any one of these steps, it's not continuous. Just a little bit about language here. So when I say for example, is, I don't know, f of x equal to 2x plus 3 over x minus 1. If I ask the question, is f of x equal to 2x plus 3 over x minus 1 continuous? What's the answer? Is it continuous? Well, the not very nuanced answer is no, it's not continuous. Where is that function discontinuous? Exactly. So the very, very not nuanced answer is no, it's not continuous. But the better answer is, but f of x is continuous everywhere except for 1. So we say it's continuous on the domain negative infinity to 1 union 1 to infinity. But in general, I should point out, if someone is very broadly asking about the continuity of a function, unless they're being more specific, if it's discontinuous anywhere, we say the function is discontinuous, even if it's mostly continuous everywhere. So if a function is discontinuous at one point, we call it discontinuous. Yeah.
If something is broadly asking if like one of the trig graphs is like if it's a tan graph,
Tangent,
would
yeah.
that would that be considered generally?
I would say if you asked me, is the tangent function continuous? My answer would be no. It is not continuous because it is undefined at many points. But if I was trying to be more specific about my answer, I would specifically say tangent of x is continuous everywhere it's defined. So as long as tangent exists, it is definitely continuous there. So yeah, it really kind of depends on how they're asking the question. But technically, any function that's undefined somewhere, it is not continuous there. So it's not continuous in general. But yeah, it's kind of right. It's not asking if a function is continuous is not a very good question. Because to be continuous, it has to be continuous on the entire interval of continuity, or on the entire interval that it could be defined on, which is everywhere. So it's usually more typical to ask, is a function continuous at a particular point? Because that's a question that makes more sense to answer. So, yeah. Sure. So let's look at this example. I used to do all this writing like this, right? I was over the summer. I was writing, and last year I was writing on the whiteboard in that room. Now all this using my hand muscles is different. Okay, so here's the function. F of x is 6 over x plus 2 plus e to the 5x when x is less than 0. It's 4 times cosine of pi x when x is greater than or equal to 0, less than or equal to 1. And it is x to the 17th power plus the cube root of x plus 6 when x is bigger than 1. So aside from 0, 1, and 0 and 1, is there any other place where this function could be discontinuous? Well, let's look at this first piece. Is there anywhere where this first piece might be discontinuous? Yeah. And so if -2 were not, so let's pretend like this was x greater than 0 for just a second, then the function, we wouldn't have to worry about -2 because -2 is not in the domain there. But this one definitely is discontinuous at -2 because it's defined to be this function when x is -2. So f of x is certainly discontinuous at the following points. X equal to -2. What about this middle piece? Is 4 cosine of pi x generally discontinuous anywhere? No, it's a cosine function. Yeah, the insides are a little different, but there's nothing that making anything undefined. So this cosine function is definitely continuous everywhere. How about this? Well, at least everywhere it's defined. How about x to the 17th plus the cube root of x plus 6? Is there anywhere that could be discontinuous? Well, it's not exactly a polynomial because I don't have positive integer powers of x, right? That cube root of x is a little bit disconcerting. So is the cube root of x ever discontinuous? If it was a square root, it would be. If the square root isn't defined for lots of things, right? If x is negative. But the cube root totally fine. Cube root you can take a positive or negative. So this thing certainly seems to be defined everywhere. This whole thing is continuous everywhere it's defined. And most roots, as long as they're defined, are continuous on their domains. All roots, actually. Now we come to the interesting point, which is this thing continuous at 0? And is this thing continuous at 1? Because when you change from one piece to the other, you have the possibility that the limits aren't going to match up. So that's usually what you're being asked about when you have a piecewise function. Is this function continuous at the changing points, where you change from one piece to the next piece? And I should probably move this here. All right. So we're going to ask, is this function continuous at x equal to 0? Well, I'm going to do the three things. I'm going to check f of 0. So f of 0, I'm going to pick the middle piece to use because that's where x is equal to 0. So f of 0 is going to be 4 times cosine of pi times 0. Cosine of 0 is 1. 4 times 1 is 4. Now we're going to talk about the limit. So does the limit exist? And almost without doubt, when you have a piecewise function and trying to find the limit, you have to do both sides. So we're going to do, so here's the thing. We know the limit from the right, or I should say the limit that's going to use the same piece that we just used should have the same value. So the limit is x approaches 0 from the right-hand side of f of x, while the right-hand side of 0 uses this piece right here. The limit is x approaches 0 from the right-hand side of 4 cosine of pi x. And then we plug in 0 and we get 4. Yeah, okay. And then we're going to look at the limit as x approaches 0 from the left. And then if we're on the left side of 0, we are using this piece where x is less than 0. So we're going to do the limit as x approaches 0 from the left of 6 over x plus 2 plus e to the 5x. And it's typical, whenever you're evaluating the limit, the first thing I'm going to do is just try to plug in what x is approaching. So I'm going to get 6 over 0 plus 2 plus e to the 5 times 0. That's going to be 6 over 2 plus 1, which is 4. Great, the limit exists. The left-hand side and the right-hand side are the same. So the limit as x approaches 0 of f of x is 4. And then I usually like to write something at the end like f of x is continuous at x equal to 0 because the limit as x approaches 0 is equal to f of 0. So the function is continuous at 0. Because the limit exists, the function exists, and they're equal to each other. Now we're going to check 1. And typically when I write these sorts of questions, usually one of the places where you have a change, it's going to be continuous, and one of the places where you have a change, it's not going to be continuous. It's kind of, it's not always going to happen. You can't count on it happening every time, but it's how a lot of people write these questions. So looking back at our function here, now we're going to look at x equal to 1. So f of 1 is going to be 4 times cosine of pi times 1. Cosine of pi is -1, so this is going to be -4. If we look at the limit, we know the limit as we approach 1 from the left is going to be the same value because it's using the same piece. So I like to write that part first. I don't know why. It feels like maybe it's more work, but it's okay. So limit as x approaches 1 from the left of f of x is the limit as x approaches 1 from the left of 4 cosine of pi times x, which is going to be -4. Yeah. And then if we look at the limit from the other side, limit as x approaches 1 from the right of f of x, we're going to use this piece where x is larger than 1. That's going to be the limit as x approaches 1 from the right of x to the 17th plus the cube root of x plus 6. And that is not going to be -4. It's going to be 8. 1 plus 1 plus 6, yeah, 8. So this function is not continuous at 1. Yep. Not continuous at x equal to 1. And now, typically, a lot of the time, your teachers want to ask you in what way your function is discontinuous. So in addition to saying it's not continuous at 1, it's not continuous at 1 because the limit does not exist. So this function that we started with here, it's discontinuous at -2 and at +1. Sorry, you can't see that. Apologies. Or another thing we could write is that f of x is continuous on the interval from -∞ to -2, union -2 to +1, union +1 to infinity. Which is often what people like to ask for, is where is the function continuous? So whenever someone asks you, where is something continuous? The question you should really ask yourself is, well, where is it not continuous? And then say everything else but that. That is really what, no one is ever really asking you to actually identify every single point where something's continuous. They're asking you to identify the very few points where it's discontinuous and then take those away from everything else. So that's discontinuity for the most part. Let's look at another example. So I'm going to ask the question broadly, is f of x equal to x squared plus 4x minus 12 over x minus 2 when x is not 2, and 3 when x is 2, is this function continuous? So what am I really asking? Well, we know that this rational function is definitely continuous everywhere except for where? Right? This function on its own without that part down there would definitely be continuous everywhere except for 2. So when I'm asking if this function is continuous, I'm really just asking, is it continuous at 2? Because I know it's continuous everywhere else. So let's talk about 2. So first things first, what's f of 2? Well, it's definitely defined. It's defined to be 3. Second thing second, I'm going to find the limit as x approaches 2. Now, in this case, I don't need to do a two-sided limit because on the right of 2 and on the left of 2, the function is the same thing. It's x squared plus 4x minus 12 over x minus 2. So I'm going to simplify like I usually would do 3 0 over 0 type of limit, which this is. And I'm going to factor. I know that the top should have a factor of x minus 2. So when I plug in 2 to the top, I get 4. Oops. I don't actually. Yeah. Oh, no, I didn't. Yeah, sorry, brain. I was not multiplying correctly. I get 4 plus 8 minus 12, which is 0. Sorry, I was seeing 4 plus 4 somehow. I was like, oh, that's 8 minus 12. That's not 0, but it is 0. Do the math correctly. It's a good piece of advice there. I know the top factors is x minus 2 times something. And the other piece is going to be, it's got to be x plus 6. I've got no other choice. So then that's the limit as x approaches 2 of x plus 6, which is 2 plus 6, which is 8. Great, the limit exists. But then 3 is not 8. 8 is not 3. So we say that f of x is not continuous at x equals 2 because the limit as x approaches 2 of f of x does not equal f of 2. graphically, it looks something like this. Right, there's your function, except at 2, it's defined to be way more. So removable discontinuity, right? A removable discontinuity is the kind of discontinuity where if you move that one point to somewhere else, you could make it contiguous. Whereas the previous one we did was a jump discontinuity, right? Where if the limit from one side and limit from the other side are not matching up, you can't just like move one point to make it contiguous, right? You have to like shift the whole function down, which is not so easy. Did you have a question?
Yeah. How are you sure that the first function on the first function that you can figure out knowing that one of the factors is x minus 2?
Excellent question. I'm sure because when I plugged into the top after I did it right, when I plug in 2 to the top, what do I get? 4 plus 8 minus 12 is, I think it's 0. 4 plus 8 is 12, 12 minus 12 is 0. So the thing is, when you plug in a number and you get 0, if it's a polynomial, you know that x minus that number has to be a factor. This is kind of, it's definitely, I think it's the fundamental thing of algebra. Basically, if f of x is a polynomial, here's something that's true. F of c is equal to 0 if and only if x minus c is a factor of f of x. Which makes sense, right? Because the thing is, polynomials do factor. So if you're going to plug in c and the whole thing's going to equal to 0, x minus c has to be one of the factors. Because if it's not, then you can't actually get 0 when you plug in c because it does have to factor into some pieces. So that's what I'm using. I'm using the fact that, oh yeah, I know if I plug in 2 and I get 0, x minus 2 had to have been a factor. Which is really convenient when you're trying to factor something that's difficult. For example, let me make up an example here that's terrible. Let's not make it too terrible, James. Sure. So if I was trying to find the limit as x approaches, sure, let's actually, I am going to make it terrible. Sorry. Let's do that instead. Sure. As x approaches 2/3 of x minus 2/3 on the bottom, just to be easy. And what terrible thing we have on top here? 6x squared plus 9x minus 4x plus 5x minus 6. So this looks awful, but it's not as awful as you think. Oh, sorry. There. So is this a 0/0 type of limit? Well, I know the bottom's 0. Is the top 0? Probably. We should check though, right? Because if it's not 0, we know it's one of those non-0/0 ones with a limit some sort of infinity. But if we plug in 2/3, we get 6 times 4/9 plus 5 times 2/3 minus 6. Oh, that's terrible. 6 times 4/9, you can cancel a 3. You get 2 times 4/3, so you get 8/3 plus 10/3 minus, yep, that's 0. So it's a 0/0 type, but specifically, when we plugged in 2/3, we got 0, which means we can factor. We can definitely factor out an x minus 2/3 from the top. This one's not quite as nice as the other ones, but it's still going to work out just fine. I hope. I know I have to have a 6x here. A 6x times x has to give me a 6x squared. Actually, I should back up. I know x minus 2/3 is a factor because when I plugged in 2/3, I got 0. And then I know I have to have a 6x here because 6x times x is 6x squared. And I know I need to have a, let's see, 2/3 times something to give me 6. Okay, 2/3 times what equals 6? 6 divided by 2/3 is 6 times 3/2, which is 9. And it needs to be a positive 9. And that's how it factors. Now, actually, that's not how I would really factor it. If I was actually factoring this, I would have made, instead of making this x minus 2/3, I would have made that a 3x minus 2, and that would have been a 2x plus 3. But okay, it still works. And then you can cancel these, and then you plug in 2/3 and you get 6 times 2/3 plus 9, which is 13. So that's what I mean when I say that, right? If you know that something plugged in makes it 0, you know that x minus that thing is a factor for a polynomial. It's not true for other kinds of things necessarily. Right. Also, if you have questions in the chat, don't hesitate to write a thing if you want to see a thing. The water break here in a second. All right. So really, there's not a lot more to continuity other than that, right? Continuity is really just show the function exists at the point, show the limit exists at the point, show that they're equal to each other. If none of those things work, not continuous. Sometimes people talk about other things. Let me mention one or two things here, and then we'll move along. So here's an example. We would say that f of x equal to the square root of 9 minus x squared is continuous on the interval from -3 to 3. Here's what it looks like. It's the top half of a circle of radius 3. It looks like that. And we do say that this function is continuous at 3 and continuous at -3, even though it's not defined on the other side of 3 or the other side of -3. So functions like this, specifically, we say that f of x equal to the square root of 9 minus x squared is continuous at x equal to 3 because f of 3 certainly exists. And when we talk about the limit, well, when functions are defined only on one side of a value, we're going to say, well, the limit as x approaches 3, it really only makes sense to talk about the limit as x approaches 3 from the left because the function isn't defined on the right side of 3. So really, we're only talking about this, and that's equal to the limit as x approaches 3 from the left of that. And that's going to be 0. Really, what we would say about this function is that it is less continuous at 3, meaning the limit from the left side is equal to the function value. The limit from the right side doesn't even make sense to talk about. But I just want, and then this is probably a very, very, very tiny thing that's not that important, but I know some people kind of emphasize it sometimes, so I just want to mention that this function, we definitely would say, okay, yeah, as far as we're concerned, even though we would say that this function is technically, it is left continuous at x equal to 3. And similarly, it is right continuous at x equal to -3. We just make a blanket statement that that's continuity, right? If a function isn't defined on the other side of that number, then we're just going to talk about it being continuous at 3, even though the limit doesn't exactly exist in the way we usually talk about it existing, right? You can't say for 3, the limit from the left and the limit from the right are the same thing because the limit from the right doesn't make sense to talk about. Don't sweat this too much. This is just something that is a very, very minor part of continuity. But if you're talking about the interval where a function is defined, being where it's continuous, then this kind of applies. Another example that often is a kind of a more typical example would be something like, we would definitely say that f of x equal to the square root of x is continuous on its whole entire domain. I mean, right? Doesn't it look continuous on its whole entire? Oh, you guys, like, if you could see it, it would, yeah. Doesn't it look continuous on its whole entire domain? Right? I can start it here and I can draw the whole thing without lifting my pen off the paper. It is continuous on its whole entire domain. But it should be noted that at 0 specifically, you can only talk about the limit from the right-hand side. So we can say, oh yeah, the limit as x approaches 0 from the right of f of x is the limit as x approaches 0 from the right of the square root of x, which is 0. And the limit as x approaches 0 from the left of the square root of x has no meaning. Because that function is not defined when x is less than 0. So if a function is only defined on one side of a particular value, we talk about it being continuous at that value, even though it's maybe only, in this case, right continuous, because the limit as x approaches 0 from the right is the same as the function. Again, not something to get too caught up in, but you might start questioning, well, look, the limit doesn't exist from the other side, so it's not defined, so the limit doesn't exist there, so it's not continuous. Well, that's not the case, right? Even though the limit from the other side doesn't exist, we still say this function is continuous at 0. You could say, although it'd be weird, that this function is discontinuous at -1, but we already know that because it's not defined at -1. So, yeah. That's why I like to say most functions are continuous on their domains, because they are. Yeah. Has anyone in, what's his name? Jacob's class, Anthony Jacob?
Yeah.
I was looking at the solutions that from the practice midterm that were sent out this morning. Some of them look a little bonkers, I gotta say. Like some of there was one question, I don't remember what it was exactly. I think there was one question, just as a point. There was like the limit as theta goes to 0 of, I think it was like cosine of theta minus tangent of theta over 2, or something like that. And the way you should do this, unless your teacher has specifically said he wants you to do something else, but I have to imagine these solutions were written by a TA. Here's how you should do this question. What's tangent of 0? What is tangent of 0? 0. What's cosine of 0? Done. That's how you should do that question. Don't make it more difficult for yourself unless, again, your teacher is specifically saying you have to. Yeah, I don't know what was going on with a lot of that, but yeah, I don't know. Also, the other thing I noticed in that I just wanted to address was I saw them talking about how it looked like they were using the precise definition of a limit for continuity. So they were saying something on the exam about how they're using delta epsilon to show that f of x was continuous at a point. And that's not usually what we do with delta epsilon. We usually use delta epsilon to show a limit exists, not that the function is continuous. Because again, when you're talking about delta epsilon, you don't actually care. When you talk about a limit existing, you don't actually care what's happening at the point. So I don't know. If I was in that class, I might have some questions for the teacher or the TA or someone, but the solutions just looked a little concerning to me. So I don't know. There was also another one where it was clearly the limit as x was approaching 0 or theta was approaching 0, but it said theta was approaching pi. I think it was like 1e. It looked very kind of, well, yeah. So that one was approaching the wrong thing. But if I were in that class, I would encourage you all to maybe ask some questions because some things just look a little. If I was a teacher, I wouldn't expect my students to be writing those answers as the answers to the test. Right? Yeah. So I would ask them, I would ask my teacher, is this what you really want? This doesn't seem like is that what you've learned in class? I hope not. I hope you've learned stuff like this, you should just plug in 0 and no.
Really complicated.
But that's terrible.
Yeah.
It's not wrong to do it this way. Yeah. Okay. Well. Yeah. So I guess then I would ask him, is it okay to do it this way? Because It should be. There's nothing wrong with doing it this way. But your teacher might have different things to say about that. Let's look at one more continuity thing. Yeah, and then intermediate like them. And I'm going to need to grab some water in a second. So let's do, how about I give you guys a question actually? So I want you to find, you also all are welcome to take a bathroom break whenever you need to. You don't have to ask permission. You can go to the bathroom, get water whenever you want. Find A and B so that this function equal to 2x cubed plus 1 when x is less than 1, ax squared plus b when x is between 1 and 3, and 4x minus 1 when x is greater than 3. I want you to find the values of a and b so that this function is continuous everywhere. And I will point out it is already definitely continuous everywhere except for 1 and 3, because each of these pieces of this function are polynomials. Right? They all have powers of x that are non-negative integers. Third power of x, second power of x, first power of x. No fractional powers, no negative powers. So all we have to do is worry about 1 and 3. So we need to find values of a and b to make this continuous at 1 and at 3. And so what I would specifically focus on here is that here are the things you need to do. You need to show or to find a and b so that the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. And also, you need the limit as x approaches 3 from the left to equal the limit as x approaches 3 from the right. All right, I'm going to go grab some water. You guys start working on that. You can also take a break if you need to. I'll be back shortly. Well, it looks like those solutions might be getting revised because the link to them is no longer working.
We have a midterm tomorrow.
I know, yeah. Yeah, so here's what I'll say about this, is it's very tempting to just try and make them equal to each other right away. So here's what I'm trying to say that teachers might not be okay with you doing. Even though it's what you essentially want to do, it's really like if you just say f of 1 is 2 plus 1 and f of 1 is a plus b, so that's equal to each other, you might get dinged. People want you to recognize that we have to talk about the limits being equal to each other. So even though we're going to get there, right, I'm definitely eventually going to be like, oh yeah, I need this and this to be the same when x is 1. So I definitely need 3 to equal a plus b. I really want you to show these steps here. We need to show that, oh, the limit as x approaches 1 from the left of f of x is going to be the limit as x approaches 1 from the left of 2x cubed plus 1 And you actually need to, right, you want to write the x there, not plug in the 1 until the next step and get, oh yeah, it's going to be 2 times 1 plus 1. And we need that to equal the limit as x approaches 1 from the right, excuse me, of the function, which is that, which is going to be a times 1 squared plus b, which is a plus b. So we're getting 3 equal to a plus b. But I do really think that if someone asks you a question like that, it's in your best interest to show that, oh, well, you need to find the limit from the left and the limit from the right and set them equal to each other and show those steps. And then we're going to do the same thing over here. We need the limit as x approaches 3 from the left, which we're going to be using this piece, the ax squared plus b piece, equal to the limit as x approaches 3 from the right, which is using the 4x minus 1 piece. And then on this side here, we're just going to plug in 3 for x, and we're going to get 9a plus b. And we're going to plug in 3 for x, and we're going to get 12 minus 1. But I do think showing these steps is worth your while, and probably worth some points if someone's asking a question like this on a test. So then we would use these two equations and two unknowns to solve for a and b. And what I would probably do, normally I would probably say I'm going to solve this for a and then plug it in over here. But I might happen to notice that both of these have a single b. So solving for b is actually probably the slightly easier way to do this. So if I solve this for b, I'm going to get b equal to 3 minus a, and then I'm going to jam that in there and get 9a plus 3 minus a equal to 11. 9a minus a is 8. A plus 3 equals 11. So 8a equals 8. So a equals 1. And then b equals 3 minus a, so b equals 2. That's it. But yeah, the whole point here is that we are using the fact that we know that for these places where you switch from one piece to the next piece, the limit from the left and one from the right have to equal each other. And so we're setting those limits equal to each other and then solving for the values of anything that make it true. All right, let's talk about the intermediate value theorem. IVT, as most people like to say. And so the very kind of basic idea about the intermediate value theorem is that function is continuous on an interval. You get all the y values from whatever the lowest y value at one end is to the highest value at the other end is. You get everything in between, if the function is continuous. Let's draw a picture. The intermediate value theorem. Nose is really itchy. People will abbreviate this as IVT, so just be aware. So the idea, okay. So if f of x is continuous on some closed interval AB, then it achieves or it takes on or it equals every y value at least once, maybe more than once, but at least once between f of a and f of b. Okay. To me, it's much easier to think about this graphically. So here's the idea. Let's say you've got some function. We know from a to b, it's definitely continuous. Maybe it looks like this. And over here is f of a. And over there is f of b. And we know that for all the y values between f of a and f of b, the function is equal to those y values somewhere for x values between a and b. So specifically, if you want to pick some, I think a lot of textbooks use like a capital N. I'm going to use a y naught because that seems more typical, right? There's definitely, for any value between f of a and f of b, there is some value c between a and b, right? That's really kind of the crux here, is that it's not just that the function is going to equal that y naught value somewhere, it's that it's going to equal that y naught value somewhere where your x value is coming between a and b, or x values in the interval. That's kind of it, that they have to have one. So said another way, if f of a is less than y naught and is less than f of b, right, if you have a value between your top value and your bottom value, there must be a number c between a and b where f of c is equal to that y naught value. That's all it says. You get every y value from here to here. And it has to be true, right? Because if you start here and you end there, right? Look, right? We start there and we end there, and there's no breaks. I have to hit every y value between there and there. I might also hit other ones down there and up there, but I know for sure I have to get every value between f of a and f of b. There's no other way the function can be continuous. So the kind of result of this is that we can use this theorem to show that equations have solutions. That is the main use that we, anyway, make use of the intermediate value theorem. Because we're going to show things that are hard, or maybe even, I don't want to say impossible, well, maybe impossible to find the actual solution to. We can still show that there is a solution. But I should stress, when you're asked to show there's a solution using the intermediate value theorem, it typically means you're not actually going to find what the solution is. And you don't need to, because you're not being asked to. So I want to show that x cubed plus 2x minus 5 has a solution. Sorry, that's not a good question. Solution to what? I could use different words to say it has a 0 or has an x-intercept, but I should actually write it more typically, which is that show that x cubed plus 2x minus 5 equal to 0 has a solution. Now, if they're nice, they'll give you an interval. I didn't. I'm not that nice. If they don't give you an interval, you just make up numbers until something works. So if you're trying to show something is equal to 0, if you know it's continuous, if it goes from a negative to a positive, it has to pass through 0. There's no other choice. So our goal, well, one, before I say our goal, whenever we're trying to do this, if it's not equal to 0, bring everything to one side so that it is equal to 0. And then after you're saying, I want to show that this equation equal to 0 has a solution, our job is to find a value where the function is negative and the value where the function is positive, because then as long as it's continuous, it has to go through 0. So note, and this is where I would encourage everyone to, whatever you're setting equal to 0, call it a function name. I'm going to call it f of x. Note that f of x equal to x cubed plus 2x minus 5 is in fact continuous. And you could say it's continuous on the interval that we're about to find as soon as we find it, or you could say it's continuous everywhere, because this one is continuous everywhere. Some functions we have to look at won't be continuous everywhere, but they'll be continuous on the place we need them to be. This one's continuous everywhere. So then I'm going to start plugging in values of x. And I'm just going to pick easy stuff. I'm going to usually pick 0 if it makes sense to. F of 0 is 0 plus 0 minus 5, negative 5. And then I'm going to try and pick a value. Well, since this one was negative, I'm going to try and pick something else that makes it positive. What should I try? -1 is not going to cut it because -1 cubed plus 2 minus 5 is going to be negative still. I should go the other way. Like any number that's bigger than 0. Tell me one. Sure, f of 1. Excellent. So playing a 1, I get 1 plus 2 minus 5, which is, oh, it's still negative. Let's try for the next one. Let's try 2. So basically, keep trying stuff until you get something that's the opposite side. So try 2, I'm going to get 2 cubed plus 2 times 2 minus 5, which is 8 plus 4 minus 5, which is 7, which is greater than 0. And now you kind of have a choice, I guess. You could pick either one of these to be your other endpoints. A lot of the time, people like to get kind of the tightest interval possible if they're trying to find the interval. So since we found f of 1 being negative, I would probably say that that's my -1. I mean, they're both negative, obviously, but like these are the ones I'm actually going to use. So then here's all we have to say now. By the intermediate value theorem, since I'm really just repeat what I wrote in parts 1 and 2. Since f of x is continuous, and we see that f of 1 is negative and f of 2 is positive. Sorry, that's right, f of 2 is positive. Then there must be some number. What do we call it? We usually call it C. I don't know why, but C is what we usually call it. We don't know what it is. Where does C have to live? What numbers does C live between? 1 and 2. Such that f of C is equal to 0. Or in other words, C is a solution to x cubed plus 2x minus 5 equal to 0. I don't think you need that last sentence, but I just want to make it extra clear what we're finding. So we showed that there has to be a solution to this function equal to 0. And we were pretty good about where it lives. C is some number between 1 and 2. Graphically, here's what's going on. So graphically, we know that f of 1 is -2. And f of 2 is +7. And since the function is continuous, I can't hop over the x-axis. I have to cross it, right? I have to actually be like, okay, it's going to do something like that. And somewhere between 1 and 2, there's my solution. I don't know what it is, but I know it lives between 1 and 2. Okay, so that's really most of the gist of the intermediate value theorem. Yeah, exactly. If we're not given an interval, we just plug numbers into the function until we find a f of x value that's positive and negative. Exactly. Let's do one more example because that one can, well, yeah, let's do one more example. So we want to show that, yeah, cosine of x equal to x. This is kind of a pretty classic example. So the cosine of x equal to x has a solution. Sure, I'm gonna, yeah, let me think for a second here to make sure. Yeah, that should work. On 0, 1. Let me double check because I always forget. I need to just make sure that I'm not doing something stupid. I feel like that's right, but now I'm like, oh yeah, we're good. Okay, that's it. So don't do this. I'm gonna instead, we want to show that f of x equal to, I don't want to show that this is equal to that. I want to show that cosine x minus x has to equal 0. Because that's going to be way easier. Right? So always be rethinking of the thing you're trying to show the solution to as something equal to 0. And it can either be cosine x minus x equal to 0, or it can be x minus cosine x equal to 0. Either way is fine. To show that this has a solution in 0, 1. Okay, so typically what we do now is we use the endpoints. So f of 0 is cosine of 0 minus 0, which is 1 minus 0, which is 1. And f of 1 is cosine of 1 minus 1. What's cosine of 1? Good question. Oh, I don't know what cosine of 1 is. You shouldn't know what cosine of 1 is. Like, it's not a value that anyone should know what cosine is. So what do? There's probably 2 different ways you can go here. One way, which is probably the more typical way, is pick a value less than 1. Right? We just have to show that there's a solution somewhere in this interval. Well, we can make the interval smaller and that would still be fine. You can't make the interval bigger because then you're maybe not in the place you need to be, but you can definitely make it smaller. So what's a number that's smaller than 1? Well, actually, in background, what are numbers that are easy to take cosine of? Or we're supposed to be able to take cosine of anyway. Like cosine of pi over 6. What's another number we should be able to take cosine of? Pi over 4. What's another one? Pi over 3. But pi over 3, too big. Pi over 3 is bigger than 1. That's outside of the interval that we're looking at. So I would pick the biggest thing, because I don't want to shrink the interval too much. And I think pi over 6 actually doesn't work for us. I'm going to pick the biggest thing that I still know how to take cosine of. So I'm going to instead say, let's make this smaller. Let's say we're going to go 0 to pi over 4. Water on my nose, really like not going away. Okay. So instead, I'm like, I don't know, but I definitely know that f of pi over 4 is cosine of pi over 4 minus pi over 4. And cosine of pi over 4 is what? Oh, it's not pi over 4. So it is so the angle is pi over 4. We're trying to take cosine of that. So say that one more time. Exactly, right? Cosine of pi over 4 is the same as cosine of 45 degrees, and cosine of 45 degrees is root 2 over 2, or radical 2 over 2. Okay. Is that positive or negative? I mean, if you get out a calculator and figure it out, but the the faster thing to do, because my calculator is not here, is to get a common denominator and say, okay, that's 2 root 2 over 4 minus pi over 4, or 1/4 2 root 2 minus pi. Okay. Is 2 root 2 bigger or is pi bigger? Pi is bigger because root 2 is about how much? 1.4. 2 times 1.4 is 2.8. So we've got about 2.8 minus pi, and that's definitely going to be negative. So that's one way to go, and it totally works. And then you can say, okay, then by the IVT, and it is true that f of x equal to cosine x minus x is continuous on the interval from 0 to pi over 4. It's really continuous everywhere. When you add or subtract continuous functions, you get a continuous function. So this is continuous on the interval. There must be a number c in the interval such that f of c is equal to 0. So it went from being negative at pi over 4 to positive at 0. Oh, sorry. And I'll just mention, since we showed there was a solution in the interval from 0 to pi over 4, there must be a solution in the interval from 0 to 1, because the interval from 0 to pi over 4 is contained within the larger interval. A different way to go that is also valid here is to remember that what's the biggest cosine can ever be? 1. Is cosine of 1 equal to 1? No, if it was, we would know it. It's not. Cosine of 0 is equal to 1. So remember, like in the first quadrant, here's the angle 0, here's the angle pi over 2, and cosine goes from being equal to 1 at 0 to being equal to 0 and pi over 2. So as the angle gets bigger, the cosine value gets smaller, at least for sure in the first quadrant. And 1 is definitely, well, I should say 1 radian is definitely in the first quadrant. Right? It's less than pi over 2. So you can be assured that, oh, well, cosine of 1 is positive, but it's definitely not equal to 1 because cosine of 0 is where we get 1. So what we could have said, and this is a little bit, I don't know, it's a little bit more, we have to think a little bit. Cosine of 1 minus 1 is definitely less than 1 minus 1, which is 0. That also works. That's probably how math teachers might show it because they're like, oh, yeah, you can say this. But either way, it's fine. That's most of what we do with the infinite theorem, is we use it to show equations have solutions. I have no idea what the solution to this equation actually is. It's something between 0 and pi over 4. That's all I got. Just as one more note here, one more, let me see. That would still work. It would have also worked if we used pi over 6, but it's a little tighter there. So we use pi over 6. Cosine of pi over 6 is, oh no, it doesn't work to use pi over 6. I'm thinking of the wrong numbers. So if you use pi, right, if you go too far to the left, if you make your interval too small, you don't get the place where the solution lives. So pi over 6 actually wouldn't work here. Pi over 4 is kind of the only good choice for a value there. What time is it? It's 11:30. Okay. So before we start talking about the limit definition of the derivative, because that's where we're going next, is there any questions you want to ask? Like, I know some people, a lot of you probably have a midterm coming. I know for sure some of you do. I imagine most of you probably have a midterm coming up in the very nearest future. You guys have any questions? I'll give you a minute. For those of you on Zoom as well, are there any questions you would like to ask? Doesn't have to be specifically about your midterm, but is there anything that's on your mind that you're like, I would really like to see something like blah? Yeah.
Is finding the range on a composition actually make like or filming?
No, it's not. Do you have an example in mind? I can make one up if not, but okay, that's fine. So let me just make sure. I'm just not quite exactly sure. So can you help me make something up? Or can we like, yeah, because I'm not exactly sure what we're looking for here. Sure. The range can always be a little tricky depending on what we're dealing with. If anyone else has something, you're also welcome to ask while she looks for that. Yeah.
Can we talk about dominant terms?
Yeah, sure. I saw another hand over here somewhere. Yeah.
So I think this is just a clarifying question. So for find horizontal asymptotes, you plug in negative infinity and positive infinity.
We take the limit, yeah, as x goes to either positive or negative infinity.
And then for vertical asymptotes, you plug in 0.
You find where with one exception, you find where the denominator is here. But we'll talk about that as well. These all go together. Dominant terms and horizontal asymptotes are kind of two sides of the same coin. Did you find your example yet?
Yes, so f of x is the square root of x plus 1. G of x equals 1 over the quantity of x plus 4. H of x equals 1 over x.
Okay, and what are we being asked to find?
Find the domain and the range of equation of f of g of h.
So, okay, domain and range. F of g of h. All right then. Of x. So let's write out what it is. So f of g of h of x is f of g of 1 over x. And then that's going to be f of, so g of 1 over x is going to be 1 over x plus 4. Before I even do anything else, what is x not allowed to be? For sure, 100%. X can't be 0. And I will point out, whenever you have a composition of functions, before you do any simplifying, you should look for the domain. Or another way I'm going to say this is, the inner function, the innermost function's domain always has to be observed. So the innermost function is h of x. Its domain is everything except for 0. We definitely don't get 0. We might also not get other things. But we definitely can't have 0 in the domain, even though when I simplify this, it's going to look like 0 would be all right. And then f of that is going to be the square root of 1 over x plus 4 plus 1. Oh boy, the doozy. All right, so definitely x can't be 0. And then we also can see that this denominator shouldn't be 0 as well. So we also need to say, okay, 1 over x plus 4 shouldn't be 0. So 1 over x shouldn't equal -4. So x shouldn't equal -1/4. Great. And then we also need that whole thing inside to be non-negative. So we also need 1 over x plus 4 plus 1 to be greater than or equal to 0. Now this is where things are a little dicey, because as soon as you start multiplying by variables, it's really a bad idea to multiply an inequality on both sides by a variable. The reason why it's a bad idea is because, is x positive or negative? We don't know. It could be either. And if x is negative and you multiply both sides by x, you have to change the direction of the inequality. I don't want to have to worry about that. So I'm really going to do my best to avoid multiplying anything by x or dividing anything by x, which is going to be kind of terrible, but that's all right. So I'm going to do a common denominator here. I'm going to have 1 over x plus 4x over. It is okay to multiply 4 by x over x. That's not multiply the whole side by x. Okay, and then I'm just going to simplify this before I say it's greater than or equal to 0. I've got 1 over 1 plus 4x over x, which I'm going to flip and multiply. So this is really going to become x over 1 plus 4x. You good with that? Everyone saw that there? This is just 1 plus 4x over x. So multiply it. And then plus 1. So I'm going to another common denominator, and you get this x plus 1 plus 4x all over 1 plus 4x. And I want that to be greater than or equal to 0. So simplifying a little bit, I've got 1 plus 5x over 1 plus 4x should be greater than or equal to 0. So I will point out, I totally could have simplified the insides of that to look like that. And yeah, I guess I could have. So I probably could have done this in a slightly easier way. That's all right. If I'd been, yeah, what I probably should have done, just to point out, is I could have multiplied this fraction by x over x. That would have been a nicer way to go. I was just thinking I was going to multiply both sides of the equation by x, and that was kind of but if we multiplied the top and bottom by x over x, we would have gotten x over 1 plus 4x, which would have gotten us right there without doing this dumb step here. So definitely go from there to there. But so now we've got that. And I want to point out, if we rewrite this as the square root of 1 plus 5x over 1 plus 4x, if you're not being careful, you might forget that x isn't allowed to be 0. Right? If you plug in 0 here, 0 looks totally fine. But you can't, because x couldn't be 0 over here. So that's what my point is. If you simplify something, you have to make sure you're still observing the domain of the very original way the expression was written. Okay, so when I'm solving an inequality like this, I'm looking for where either the numerator or the denominator is 0, because that's the only place the sign can change. So the denominator is 0 when x is -1/4. The numerator is 0 when x is -1/5, which is bigger or smaller? Or I should say further to the right or further to the left? Further to the right, right? 1/5 is smaller than 1/4, which means -1/5 is less negative than -1/4 is negative. Okay, so then we're gonna pick numbers, like pick something like 0. If I plug in, oh, don't pick 0. 0 is not allowed. Pick something like 1. If I pick 1, 1 plus 5 or 1 plus 4 is positive. I really don't want to try and pick a fraction between -1/4 and -1/5. It seems really silly. Instead, what I'm going to do is I'm going to be like, well, -1/5 came from this factor. This factor is raised to an odd power, which means when you go to the other side of it, or if I pick some, so I guess I could say two things. I know the sign's going to change because of the oddness of this factor. And you can either use that, or you can say, well, I'm picking something less than -1/5, which means this top part is going to be negative. If x is more negative than -1/5, 5 times it is going to be more negative than -1. And if you add 1, that's going to be negative. On the other hand, I'm picking something that's larger than -1/4. So this 4 times it is going to be larger than -1. But when I say larger, I mean closer to positive. So it's going to be not quite as negative as -1, and the bottom part's going to be positive, and negative or positive, negative. And then same deal over, let's pick something like -2, negative on top, negative on the bottom, positive overall. So what's my domain? That's everything from -infinity to -1/4. Normally I would include -1/4, except that's what makes it undefined. So no. Union, I want to include -1/5, because -1/5 makes it equal to 0, and 0 is okay. So -1/5 to infinity, right? Wrong. We don't get 0. Right? You have to remember that 0 is not included too. So tricky. And that's not even the question you asked. That's the domain. We want to talk about the range now. What time is it? Okay, we got time. So range of this really, really fun looking function. Whew. Sheesh. Yeah, I don't. So yeah, I'm assuming you're not allowed to use a graphic calculator, right? Right. So what would I do? I'd probably look at each of these domains separately. So let's look at this domain here first. If x is greater than 0, then what's going to happen to 1 over x? 1 over x is going to be also greater than 0. But can still get infinitely large. And then if I add 4, 1 over x plus 4 is greater than 4, still less than infinity. And then if I take the reciprocal, oh, geez. Ugh. That's terrible. I don't like that. I mean, it's fine. I'm sorry. You guys might like to see what I'm writing. Just let me know, really. Like if I'm off page, just say James. So x is bigger than 0, less than infinity, right? I'm looking at this part here. Reciprocal, switch the directions, take the reciprocal of everything. 1 over infinity, 0, 1 over 0 is infinity. Add 4, reciprocal, change the directions, and then add 1. I feel like, no, that's right. So at least when x is living in here, my range values, well, then take the square root of everything. Gross. My range values are between 1 and the square root of 5/4. I'm not really sure what kind of madman would ask you this question. But that's how I guess I would have to kind of try and attack it. And then I would probably do the same sort of thing for this. So watch this. So if x is between 0 and -1/5, I'm going to do the same sort of ridiculous thing I just did, where I'm going to work on this until I get it to look like that. But I'm going to do it to all the things. So I'm going to do 1 over x, switch the directions, reciprocate everything. That seems like a mistake already. Oh, so I should be careful here. This 0 is I'm on the negative side. So when I take the reciprocal of 0 here, I'm going to be bigger than -infinity. Right, because 1 over, so right, this is a slightly negative 0, whereas this 0 was, right, we're thinking of being positive here. So 1 over 0 positive is infinity, 1 over 0 negative is negative infinity. And then I would add 4 to everything. Negative infinity plus 4 is still negative infinity. Got the 4 there. And then I would take the reciprocal of that again. Reciprocal of -1 is -1. This seems like a very, very bizarre question. Reciprocal of infinity is 0. And then we would add 1 to everything. And then we would take the square root of everything. So it looks like here, I'm getting everything between 0 and 1. It seems crazy. And then, yeah. I don't want to do the last part. I mean, I'm not because like it's any harder than these parts, just because I'm done with this question. So to answer your question, this is how I would approach it. There might be a better way. I really don't know. This seems pretty awful. So yeah. Okay. Let's see. Yeah, I don't know how. So someone asked how you graph 5/4 times x over x plus 1 to the 3/4. I don't know how you would graph that really either without a graphing calculator. So I don't have a good answer to that question. But let's go ahead and talk about dominant terms for a second. So dominant terms. So if I was asking what's the limit as x goes to infinity of 2x cubed plus 5x plus 1 over 4x cubed plus 6x squared plus 3. Well, first of all, another way I could phrase this is, what's the horizontal asymptote of 2x cubed plus 5x plus 1 over 4x cubed plus 6x squared plus 3? And the way you find the horizontal asymptote is by taking the limit as x goes to infinity. And then if you were trying to talk about the dominant terms here, well, the dominant term in the numerator is 2x. 2x cubed is far and away larger than any of the terms after it. And the same thing down here in the denominator. 4x cubed is definitely the biggest thing by a long shot. It is the dominating term. So some people like to do this thing where they say, well, this is essentially the limit as x goes to infinity of, we only care about the dominant terms. And then that's just going to be 1/2. That's kind of the idea there. But it also works for, it doesn't work just for powers of x. So if you want to say like, what's the limit as x goes to negative infinity of e to the 2x plus 3 e to the negative x over e to the 4x minus 5 e to the negative x. What are the dominating terms here? Well, you might think it's the e to the 4x. And that would definitely be true if x were going to positive infinity. But x is not going to positive infinity, it's going to negative infinity. So here, the dominant term is actually e to the negative x. I think when I hear the word dominant term, I think of what's the thing that's growing the biggest, the fastest. And here it's definitely, well, in fact, e to the negative x is the only thing that's actually getting larger. E to the 2x and e to the 4x are both getting smaller as x goes to minus infinity. And here's what e to the 2x and e to the 4x look like. And as x goes to minus infinity, they both get really super small. Whereas e to the negative x looks like this. And as x goes to minus infinity, it gets super large. So the way I don't really want to do this limit, but the way I imagine some people might think you would do this limit, I mean, you say, oh, well, here are the dominant terms. And those cancel out, and you just get 3/5. If I were doing this limit, as with the previous one, so if I were doing this previous limit, what would I have actually done to all my terms? I would have divided by what? The dominant thing, x cubed. I'm going to do the same thing here. I'm going to divide everything by the dominant thing. Let's see what happens when we do that. So e to the 2x divided by e to the negative x plus 3 e to the negative x divided by e to the negative x over e to the 4x divided by e to the negative x plus, minus 5 e to the negative x over e to the negative x. And when I simplify this, I get the limit as x goes to negative infinity of e to the 3x plus 3 over e to the 5x minus 5. And as x goes to negative infinity, that goes to 0. That goes to 0. Get negative 3/5. Sorry, I forgot the negative sign here. I apologize. So when people speak about dominant terms, they're just kind of talking about what's the thing that's getting the biggest, the fastest. And so in case you're curious, I don't want to say that. Yeah. So an exponential thing is kind of always our biggest thing. So e to the x is kind of the thing we have that grows. I mean, really, a higher base would grow faster. So 4 to the x would dominate e to the x. E to the x would dominate x to kind of any power. And that would dominate x to a smaller power. And that would dominate x to the first. And that would dominate like the square root of x. And that would dominate like the 5th root. And then way on down the line is the natural log of x. So here's the way I kind of think about it. Exponential functions grow the fastest. Exponential functions dominate polynomial functions. Dominate f of x equal to x. Dominate radical functions or roots. Dominate logarithmic functions. So even the 1000th root of x will eventually grow faster than any logarithm of x. Graph them on Desmos and check it out. It takes a while, but if you zoom way out, you will see that, like, for example, the 20th root of x is bigger than the natural log of x eventually. Maybe right away. I don't actually know if it takes eventually or not, but definitely any root is bigger than a logarithm eventually. X is always bigger than a root of x. X to a power is always bigger than x to the first. And an exponential is always eventually bigger than x to any power. True. Even though it might start off smaller, it eventually grows bigger. So that's what I kind of think of when I think about functions that dominate. And it definitely is going to become, this idea of dominance, or what thing gets biggest fastest is the way I would phrase it, definitely comes back when we, in 21C, when we talk about some series tests for convergence. There's a question here, why do you choose to divide everything by e to the negative x to e to the 4x? So that's an excellent question, Rosh. If the limit had been as x approaches infinity, I would say yes, e to the 4x is the more dominant one. So I should point out that all of these are talking about as x is going to infinity. But this specific example I did here, x was going to negative infinity. And so when x is going to negative infinity, e to the negative x is the dominant thing because it is getting biggest the fastest. And e to the 4x is actually going to 0. So that's what's happening there.